And it says I'm live, and we're back. Excellent. Okay. So a couple of things as we're moving forward into this brand new month, brand new year. I believe, and I got to double check this, I believe I have 7 class periods until midterms. I have you 2 days this week. I have you 3 days next week. And then I have you 2 days during the following week, which you do have that Monday off. I could update this. So yeah, that's about 3, 4, 5, 6, 7. And then I don't know what day your midterm is, but it's going to be one of those days. But we'll figure that junk out. Yeah, 7 class periods until midterms. There's just a few key concepts that obviously I still need to go through before we get to said midterm. But what I want to do is I want to pick up with where we left off. Now, we left off with this particular problem. So what I'm going to ask you all to do, and I'll kind of hold this up. We left off drawing out a probability tree like this. I'm going to hold this up for people in the chat as well, because I know there's some people there. So if you would, please have those notebooks out and open and on that page, because I'm going to be adding more to this particular page in my notes. I'll kind of refresh how we came about drawing a tree like that with this particular problem. And then I'm going to add more to it and actually answer said question, because we ran out of time last time we were here. I'm going to briefly go over something like that. Now, eventually, I am going to be assigning a page or some problems out of the textbook. I'm going to be doing that. I left a note for myself. I'm going to be doing that before I leave the building here today, because I would like you to get some extra practice with these probability type problems. But after I go over something like this, I am going to be introducing a slightly newer concept in regards to probability, but we'll get there when we get there. So this problem says, for the purposes of making budget plans for staffing, a college reviewed students' year in school and area of study. Of the students, now this is the breakup of the class that they're in, or the year that they're in. 22.5% were seniors, 25% junior, 25% sophomore, and the rest are freshmen. And according to the picture that I drew here, oh, it's frozen, that's right. Unfreeze, there we go. Oh, it's not on the right page. There we go. Zooming out. Of the picture that I drew here, and it was a little hard, 5%, 25, 25, and then the rest were freshmen. Clearly, that should add up to 100%. Now, this problem, the very next thing that it said, I'll zoom in on this statement right here. The very next thing that it said, 40% of the seniors. That is a conditional statement. That is a given statement. Given that you are of the seniors, 40% of you are majoring in humanities. Of the seniors, 40% of you are majoring in humanities, which is why off of the senior branch, I broke up that senior branch, 40% humanities and 60% other. The given statement means that you've already walked down one of those branches. Given that you've already walked down the senior branch, what are the chances that someone would major in humanities? 40%. They gave similar statements for the juniors, the sophomores, and the freshmen, as you can see here. The freshmen, those are all given statements as well, which was the justification for filling out, I'll zoom out a little, filling out juniors like that, sophomores like that, and freshmen like that. And then came the question, the actual question that they were asking. The question that they were asking, and this comes down to the wording of the question, and this is going to be something that a lot of people are going to have issues with. What is the probability that a randomly selected humanities major is a junior? This is what they're asking. They want to know the probability of being a junior given that you are a humanities major. That is how that problem is worded. What is the probability that if you were selecting from the humanities major, that's another way of thinking about the wording of that question. As everything has been in AP Stat, the wording of the question or the wording of the conclusion means everything. We need to have properly worded sentences. This is a perfect sentence. We just have to be able to interpret it correctly. Now, if I go back to this statement right here, 39% of the juniors, that does not answer my question. That statement that I just underlined basically answers this question. Given that you are a junior, of the juniors, 39% of humanities majors. Now, if you've done any research into conditional statements and the idea that these are being reversed, there is a formula in the right mind that would ever even try to do something like that. So instead, we rely on the concept of a probability tree in order to answer this question. What I need to do is this, and this is what I'm going to add. Actually, no, I'm not going to add it to my tree just yet. I'll write it on the board. In order to answer this question, we need to utilize was basically the probability of B given A is equal to the probability of A and B divided by the probability of A. You always divide by the probability of the given event. In this case, given humanities, I have to divide by the probability of humanities. We need to figure out these two probabilities, and once we do so, we will be at our answer. But those are the probabilities that we have to figure out. Let me go to the tree. Zooming out, zooming out, zooming out. The first thing that I would like to fill out on this, I'll erase something in a moment, but the first thing I want to fill out on this is the following calculation. Make sure I got this number right. .0975. I'll zoom in on that branch of the tree, and I'll erase what I got up there because I know it's bugging some people that I left some stuff up there. What I just filled in. Come here, you. I wrote out the probability of junior and humanities is equal to, or approximately equal to 0.0975. How did one get that? How did I get that number, 0.0975? I don't know. I guess I just looked at the tree and I hoped for the best. When I literally went along the branch of junior, 0.25, and multiplied by this sub-branch of humanities, 0.39, I multiplied to get 0.0975. That gives me the probability of juniors and humanities. Now, as we said, in order to figure out the answer to this question, we needed that to should be the probability of humanities. The issue that we run into is the fact that, well, if you are a humanities major, you could be a senior, or you could be a junior, or you could be a sophomore, or you could be a freshman. If you're just looking for the probability of humanities majors, you could be one of those 4 grade levels. Do on the tree is this. Get a better marker here. Zooming in, zooming in, zooming in. I'm going to multiply again along the senior branch, and I'm going to get approximately 0.09. That 0.09 represents the probability of being a senior and a humanities major. I'm going to multiply along the sophomore branch. And I'm going to get equal to 0.1. I know I did approximately before. But that 0.1 is the probability of being a sophomore and a humanities major. And I'm going to multiply along the freshman branch. And I'm going to get 0.099. That is the probability of being a freshman and a humanities major. So look what we've done with this tree. First, I justified how I filled out the tree in the beginning. But if you multiply along the branches, you are finding the probability of two events, A and B. Senior and humanity, junior and humanity, sophomore and humanity, freshman and humanity. And as I said, if you're going to be a humanities major, you could be a senior or a junior or a sophomore or a freshman. What do you think I am going to do with these four numbers right here in order to move forward with the problem? I'm going to add them all together. And if I add them all together, hold on. Let's see. 0.09, 0.0975, 0.1, 0.099. Can't really see it that well, but just double checking my numbers. Cha-chow. I add them all up. I get 0.3865. What does that represent? What does 0.3865 represent in the context of the problem? Yeah? Just flat out humanities major. Yeah, that's what it represents. We've hit every possible scenario because it could be one of the four grade levels, but that by itself, that 0.3865 represents the probability of being a humanities major. So at the bottom, oh, bless you. If I add all four of those up, I get 0.3865. This is the probability of being a humanities major. Let me move that up so you can see what I just wrote there. Now, like we said, that doesn't answer the final question. That just gets us on our way. In order to answer said question, the probability, where are we at? There we are. Of being a junior given humanities major is equal to the probability of junior and humanity, which now I got 0.0975 divided by 0.3865, which I'll calculate in a moment. Again, the 0.0975, junior and humanity, I just multiplied along the branches. To get the probability of humanities, I needed to multiply across all four humanities branches and add them all up in order to get the 0.3865. And ultimately, thanks to the formula, I can just divide those two to get my final answer. Boom. Was this a problem where before we left, I wrote the answer on the board and I said, hey, we'll get there? Or did I not do that? Okay. I thought I did. I don't know why I did, but whatever. Final answer is 0.252 approximately. These probability trees can be very helpful. It seems tedious, but believe me when I say that this is so much better than whatever formula they would have given you. See if I can find it. I like to show for comparison what that for. Oh, there it is. Oh, yeah. Okay, here we go. I'm going to zoom in. There's something in your book called Bayes' rule, which the formula is not on the screen right now. but there's something in your textbook called Bayes' rule, where you can see at the very top, when we have the probability A given B, but want the reverse B given A. If that's the case, you could do one of two things. You could either use the probability tree, as I've outlined in this class and in the previous class, or you could utilize the following formula at the bottom of this page. Yeah, I'm not going to touch that formula. I don't know anyone in their right mind who would touch that formula. It's weird. In fact, look at the... I'm sorry, I just like the comment at the bottom. Masochist may wish to try it. It's easier to just draw the tree, isn't it? But yeah, that's in your textbook. On the very next page, they do a problem where they're literally like, yeah, let's draw the tree. And you can see the tree in the corner. You can see those in your textbook. Oh, Bayes' rule. I don't know anyone in our right mind who ever teaches Bayes' rule. Question?
Yes.
Go ahead.
So for our final answer, we got 0.25. Yeah, 0.252. Would that be like 25.2%?
Yes, 25.2%. You could either write it as the decimal or the percentage. No, that's perfectly fine. That's perfectly fine. The reason why I usually go 3 decimals is for the simple reason, if you convert it to a percentage, percentages are better off going an extra decimal, like 25.2%. You know, it's easier to compare 25.2% to 25.9%, let's say. But yeah, I like going 3 decimals, but that's me. Okay. Oh, goodness. Now, like I said, what I'm going to be assigning you in terms of a page out of the textbook for practice, purely practice type stuff, is going to be based on a lot of the probability stuff that we did before break. I wanted to wrap that up. That's what I wanted to do before break, but that's where we're at. So it's going to be based on a lot of the and the or probabilities, the tables that we've been doing. I think we spent a bunch of time with the table with like French and science and stuff like that before break. It's going to be those types of problems along with potentially a probability tree type problem. Probability trees should basically be used under 2 circumstances. One, it's helpful to organize definitely if you ever have to reverse a conditional probability. That's mainly what it's used for. So, but I will be assigning that before I leave here today. Okay. Now, like I said, I wanted to take another step forward, and it involves going a little bit more in depth with a slightly newer concept. So I am going to be giving you a header to a new chapter. This new chapter is just entitled Random, in fact, it's spelled random today, Random Variables. Today is the 5th. Don't write a 20. You know, it's weird. I wrote the 21 yesterday, and I'm like, that felt nice. You know, it just felt like, oh, yeah, I'm not going to make that mistake. You know, like every year, there's always a mistake. Like, oh, I keep writing the previous year. Not this year. I'm going to be describing to you a scenario where you play a random game. I'm not going to describe the game. The game is not so much important, but the scenario is important. Imagine a high-stakes game in which you play it twice. And the result of this high-stakes game, in playing it twice, you either win-win, you win-lose, you lose-win, or you lose-lose. And depending on which one you get, you walk away with a certain amount of money, a certain amount of profit. Obviously, you have to pay just to play the game. You have to pay a large amount of money just to play the game. Yay, oh, happy day. But then you could walk away with a certain amount of profit. So, for example, you have the event. Now, the event in question is either you win-win, you win-lose, you lose-win, or you lose-lose. Now, what result happens is based on random chance. In fact, there is a certain probability of the event happening, but we'll get to that in a moment. If you win-win, then you will walk away with a certain amount of profit. Obviously, like I said, you have to pay a certain amount of money just to play it. Let's say it's a large amount of money. But if you win-win, you could walk away with $80,000. $80,000. I don't know, perhaps you had to pay 20 just to play or something like that. If you win-lose, you could walk away with a $30,000 profit. Again, maybe you had to pay $20,000 to play, and then they gave you a certain prize amount, and you're like, yeah, cool, good for me. Same thing with lose-win. You also walk away with $30,000 profit. But if you lose-lose, then you actually lose money. In the end, you're $10,000 later. Now, so far, this seems almost too good to be true. So far, it seems like, well, I mean, clearly there are 3 events in which I walk away with a lot of money, and there's only one event where I walk away with, negative money, or I gotta, lose money. But the probability of that event happening does come into play. In fact, the chances that you win-win are only 0.06. You have a 6% chance of win-win. You have a 14% chance of win-lose. You have a 24% chance of lose-win. Apparently, if you lose first, you have better odds second time around. Who the heck knows? And you could probably figure this out just by basic math. You have a 56% chance of lose-lose. Basically a coin flip. I'm certain that you have always, or not always, but that you've heard the phrase, the house always wins. Gambling is one of the dumbest things you can do. It really is. Oh, Mr. Markey, no, I knew a guy, he went to Atlantic City, he walked away with $5,000. Yeah, I guarantee that probably happened. But for that one guy walking away with $5,000, how many people walked away with negative money? A lot more. That's how casinos thrive. You might have one guy walk away with the grand prize, but with the number of people playing and losing money, the house always wins. Just what happens. I told you guys about my dad, right? Yeah. My dad more often than not walked away with negative money. And why do it? Because it's fun and it's addicting. It's also dumb. Just saying. Don't gamble your money away. Now, here's my question to you. This scenario, and this is more of a mental exercise. If this is the scenario, on average, if every single person in this school played this game, 6% of them would win $80,000 profit. 24% of them would win $30,000 profit. If every single kid in this school played this game, and then afterwards we went up to all of them and averaged together their profits, what would the average profit be? Now, if I word it like that, it might make a little bit more sense. But the statistical way of saying it is, okay, what is the expected profit? expected is a word that means a lot in the realm of statistics. If I say, what is the expected profit or the expected winnings of this game, or losings, whatever, then there is a procedure in which you would calculate that. But if I simply said, okay, if everyone in the school played it, hey, 6% would win $80,000, 14% would win $30,000, we can average all of those together. Kind of. Now, I don't know how many people are actually playing this game. So instead, I'm going to do something like this. How the heck did I just get that number? I don't know. How the heck did I just get that number? Or that number? Oh, I'm sorry. This should have been a 4. And that should have been a 7. There you go. And then that number is correct as well. I apologize for the blobs right in the middle right here. Those are mistakes. Yeah. Fairly straightforward. That is the profit, whatever that value is, times the probability of getting that. Just multiply the two of them together. I can show you a couple of them right here. Here's 80,000 times 4,800. I'm sorry, times 4,800. My bad. 80,000 times 0.06. There we go. I'll zoom in right there. 30,000 times 0.14 times 0.24. Negative 10,000 times 0.56. Next, after multiplying the value of the event times the probability of the event, I am going to simply add them all up. And if I add them all up, hopefully you remember that symbol right there. If I add them all up, the value I get is $10,600. That's pretty solid. The question is, what is the expected, bless you, profit of the game? You get that? It seems fairly straightforward, and it is. It is. Proper interpretation of these problems is one thing. But we can expect the expected value of casino winnings. You better believe the casino is going to be positive and you are going to be negative. Oh, but what about that one person that walks away? Yeah, that's one person. Not every person. Every person on average is going to be a negative value. Here's the formula for you. That symbol that I just drew should look familiar. What the heck is that symbol? He whispered it. What was it? You all sound so excited. It's 151st Pokemon. Thank you. It's Mew. But in this particular instance of random variables, we're using it to represent the expected value of the event. E of x, E parentheses x, represents expected value of some random event, x. In this case, x is a random variable. And it equals the following calculation. Simply, you multiply together x times the probability of x in this case, and you add them all up. Yeah. Just for the sake of argument, just so you know what you may end up seeing in your textbook, because mathematicians are very creative with their notation. Oh, the glare is in the way. Let me move this a little. There we go. In your textbook, you may see something like this being a capital X and these being lowercase x's. I just wanted to point that out because sometimes you may see something like that. It's just like, well, why don't they just use a different letter? I know. Wouldn't that be great if they used a different letter? But no, they're distinguishing capital X and lowercase x. The capital X is the random variable that they're dealing with, which the random variable in this case is the event that's going to happen. You could, well, win, lose, all that other stuff, all those possible wins and losses. And then the profit, or the value of the profit, I should say, times the probability of that profit happening. And then they add them all up. It's very weird. I need to give you some definitions. You may be familiar with these definitions, but I still want to get these written down just for the sake of argument. I'm going to bullet point them. First, a random variable, I'm underlining that, would be the possible numeric value of a random event. Whenever you hear something like that, whenever they're referring to a random variable, it would be the possible numeric value of a random event. Now, the thing is, it's like, well, Mr. Mark, you said numeric value. Numeric value obviously implies numbers, but you said the first event was win-win. Win-win is not a number. I know, which is why win-win is paired with 80,000. 80,000 is the numeric value. If you can list all the outcomes, which we did, good for us. But if you can list all the outcomes, then it's a discrete random variable. I'll move that up in a moment. If you can list all of the outcomes, which we clearly did in the previous example, then it would be referred to as a discrete random variable. I don't know if you did this in trigonometry. In trigonometry, did you ever have to determine discontinuity or something like that with graphs? I see several people nodding yes. Okay. And continuity just referred to whether or not the graph, there was any holes in it or asymptotes or things of that nature. Cool. Otherwise, it's a continuous random variable. Otherwise, it's a continuous random variable. Yeah, get there. Now, I mentioned that thing about graphs and continuity and things of that nature for the following reason. I mean, obviously, if we can list all the outcomes, it's discrete. But if we can't list all the outcomes, then it's continuous. I'll just give you an example right here. Zooming in. Come on. Give me a random number between 0 and 1. 0.5. Give me another random value between 0 and 1. Okay. Give me another random value between 0 and 1. I'm laughing. Give me one more. Okay. You guys have to give me that 10 to the 10th value. This function that I have up on the calculator gives you an actual random number between 0 and 1. And another. Can I list them all out?
No.
There's no way. There's no stinking way I could do that. There's none whatsoever. Yeah, check this out. I can actually prove it to you, right? Hold on. Okay, check this out. Pick a number that's not 7. 8. Pick a number that's not 5. 4. Yell at a number that's not 0. 8 again. Not 4. 3. Give me another number that's not 3. See? I heard a 1. Not 8. 6. Not 4. 3. Question. Not question, statement. Based on the procedure that I just did, the number that I'm writing out is guaranteed not to match any number that's in that list. Guaranteed. And if I continued that procedure forever and kept hitting enter forever, I would come up with a number that is not in that list. It's really messed up to think about, but there's no way I can do it. There's no way I can list out all of them. None. It's continuous. But I digress. Okay. I'm going to write out a definition for standard deviation. And I'm going to expect that you write it down as well. But while I'm writing it down, I'm going to ask very briefly, to have those Chromebooks out and open. So I'm going to write down a definition. But I'm going to ask for those Chromebooks to be out and open for a very specific reason. Come here, chair. What? Oh, man. That stinks. There we go. For a discrete event, you can actually calculate the standard deviation, which is great. Where you could take the square root. It's really messed up. It's basically you take the deviations from the expected value. The expected value in this case being what, for our example, is like 10,600. X minus that mean, you square all of them, you multiply it by the probability of X, you add them all up, and then you take a giant square root, and then you can find the standard deviation. Meaning, on average, how much would people deviate from this, well, expected value? But it's a lot easier if you can use the calculator, which is why you have your Chromebooks open. But you can use the calculator. Now, here's what I want you to do. In your graphing calculator on your Chromebook, I want you to go to list 1 and list 2. If you hit Stat, Edit, you'll find your lists. In list 1, I want you to type in order, 80,000, 30,000, 30,000, and negative 10,000. Those 4 numbers. And in the second column, I want you to put in 0.06, 0.14, 0.24, and 0.56. Now, what's really nice about this, and I'll bring this up here so I can actually see it too. There you go. Let's see. Let me clear that out. There we go. Stat, edit. 80,000, 30,000, 30,000, negative 10. What? Ah. What I don't like about this calculator. Because I'm so used to hitting this button up here. Excel does it. Whatever. Anyway, 0.06, 0.24. Oh, sorry, not 0.24, 14. 0.24 and 0.56. Then I'm going to write this down into our notes. But if you hit Stat and tab over to Calc, you have that thing that we've done earlier in the school year called 1var stats. However, if you do 1var stats like this, it will only calculate 1var stats using L1, as you can clearly see. So if I went down to calculate, clearly that's only doing 1var stats for L1. That's not going to be very helpful to me. So I'm going to have to try something here. Comma. It won't let me do the comma. Ooh. Are you going to be able to do this? Well, 2var stats is a little... Don't do that. I'm going to show you. You don't do it. Let me do it real quick. Let me show you real quick. If you do 2var stats, these are not the numbers whatsoever. These are not the numbers that you need whatsoever. None of these numbers play out the way you want it to at all. What I actually want to get is this. And let me do it here on this calculator. And I'll show you what I mean. Because I was not prepared for your calculators. I was prepared for my calculator, which now I may have to find an alternate way of doing this. Watch what I'm about to do up here. Everyone with your eyes up here. On the regular TI-83, you could go to 1var stat, and you can literally do this. You can tell it L1, comma L2, in which it will calculate the proper expected value and standard deviation. That's what it should be. That is exactly what it should be. And you can see the standard deviation, they actually used the sigma down here. On yours? On the online one? What'd you type in? Let's do it. So hold on. Clear that. Stat. 1var stat. So you just did like second L2 like that? Yeah. So you don't need a comma. I don't think so. All snap. Didn't work. You lied to me. Everyone boo him. Okay, that was only like one person. That's so weird. I'm going to have to figure that out. But like I said, on my calculator, all I have to do is something like this. I'll have to come back to you guys with that. All I'd have to do is something like this. 1var stat L1, comma L2. That's all that I would have to worry about. If I put in comma L2 or L1, comma L2, it will do exactly what I need. It will calculate the exact expected value, which in this case was $10,600. And it will calculate the exact standard deviation, sigma, of $25,877.40. Yes. Yes. Here, fill this out for me real quick because I got to try something on the computer. Let me see this real quick. Wait, so you said you went here. You went to 1var stat, right? And then did you do anything for frequency list? No. You just typed in L2? Yeah. Like that? And it gave you all those numbers? Plus on help menu for catalog help? That seems weird to me. I don't doubt that it worked for you, but like I don't know, for mine it's like not doing what I needed to do. And like I said, 2var stats won't do it. 2-bar stats will not give you, oh, I'm sorry. 2-bar stats, well, I got it here, will not do it for me. Yes. That's so weird. Like I said, I'm going to have to come back to you guys on that because I know how to do it on my calculator. I don't know how to do it on yours. That's so weird. Okay. Chappelle. Oh, I'm sorry. Go ahead. And it worked? Oh, snap. Let's go. 1-bar stat. L2. Well, there you go.
Is that it?
Yeah, those are the numbers. That's so weird. Like I said, I'm so not used to your guys' calculator. You know, I'm so used to the handheld calculators. Yeah, apparently all you got to do is put it in the frequency list for L2, and it spits out. You can see at the top right there, if you look at the very top, X bar is your expected value, and your sigma, 25,877 and change, that's your standard deviation. Which makes sense because, I mean, if you think about it, it goes all the way from $80,000 all the way to negative $10,000. On average, people are deviating by about $25,000. I don't know. I guess this is where gambling comes into play. Think about it in your head. If the expected value is $10,600, that's the expected value. On average, that's what you would expect to win. However, there is a 56% chance that you would lose $10,000. Would you do it? Don't answer. Don't answer. It's a rhetorical question. But I'm like, you have more than a 50% chance of losing $10,000, but then on average, well, you do have a 44% chance of winning something. It's basically a coin flip at that point. Oh, it's so weird. Anyway, a couple of basic things before we leave here. A couple of basic things that I need definitions to give you. Combining two random variables. And I do have examples of this that I'm going to do with you next time. I just wanted to get the definitions down with you first. Let's say that you have two distinct random variables. Let's call them E of X and E of Y. Or just X and Y, I should say. If you have the expected values of two random variables and you wanted to find out what the combination of the two of them was, it's a simple matter of just, well, adding. It's ridiculous, but it kind of is. It's like basically, okay, you go play that game where you could possibly win $80,000. That's E of X. And now there's a completely separate game on the other side of the casino that you're going to play that has a different set of outcomes. Let's say that you're going to play both games. All right, you're going to play both games. The first game has an expected value of $10,600. The second game has an expected value of, I don't know, negative $10,000. If you played both games, what would you expect to walk away with? 600, what? Oh, I thought you said 600,000. I was freaking out for a minute. But yeah, $600. It's like, oh, you just add them together? Yes. Seems ridiculous. I know, it is. Then the difference between them. Get ready. It's the hardest thing all year. Yay, we did it. Woo! All right. How many stars have I given you this year? Really? That many? In your notes? Really? Wow. I apologize if it's been more than I expected. Here's a star for you. I try not to give out too many stars. I try not to, because it devalues them. That's basic economics. Unfortunately, standard deviation cannot be done the same way. Someone get that? Unfortunately, standard deviation cannot be done the same way. If I were to combine two random variables, two random events, if I wanted to find their expected value, yeah, combine them, add them, yeah, sure. The difference between them, yeah, sure, just subtract them. Yeah, absolutely. Standard deviation, I can't do it that way. I can't. You have to convert it first. You have to convert standard deviation into something else. Now, there is another version of standard deviation that is not used very often, except for now. And it's something called variance. Variance is something that they may end up giving you like on a stat sheet output. They may like, here's the output data and here's your variance. Oh, crap, I have variance? I was hoping for standard deviation. Standard deviation is used much more often. Yes, it is. Standard deviation is by no pun, not necessary, no pun intended. It's the standard bearer. That's what we use in order to measure, on average, how much people vary or differ from the mean. Variance is nothing more than standard deviation squared. That's all that it is. The reason why I'm referring to it in this sense is because of the idea of combining two random variables. If I wanted to add together or combine by addition two standard deviations, I would not be allowed to just add them. First, I would have to convert them to variance. So let's say you had two variances, x and y. I'll move that down just a little bit. If you had these two variances, and I wanted to combine them by adding them, yes, I totally could now. Here's going to be the procedure. If you have two standard deviations and you want to combine them, first, convert them to variance, then add them together, then convert them back. How do you convert variance back to standard deviation? Square root. Yeah. So if I had a variance of, not a variance, let's say I had a standard deviation of, I'm making this up, a 4 and a standard deviation of 9. No, I don't want to do 4 and 9. Let's do 2 and 3, whatever. Well, I would square it to get 4. I'd square it to get 9. That gives me 13. The combined standard deviation would be the square root of that number. It's similar to like a Pythagorean theorem type situation. It's very strange. But you would convert it to variance, perform the appropriate calculation, and then convert it back. Very last thing I want to write down here. Very last thing. Check this out. What about the difference between them? Well, that seems pretty simple, Mr. Markey. I mean, there's absolutely nothing that could really mess us up now based on all the other stuff that you did today. Somebody say something. Not a typo. There's a reason for that. Unfortunately, I can't talk about it now because we only got about 30 seconds left. Similar. There's a much more in-depth conversation I want to have with that, unfortunately, at a time. Now, like I said, all the stuff that I've introed to you today, we're going to get more practice with. The page in the textbook that I want you to do is going to be based on previous probability stuff that we've been doing, so you get the practice with that. And then bell's going to ring in about 3 seconds, so we'll see you then. Cool. I'm going to sign off. Goodbye, goodbye, goodbye. Go home. Goodbye.
Always on point, you're like 3 seconds.
Oh.